Thanks. And he just reminded me that he was at the University of Guelph forever ago. I can't even remember, but and Ricky was on his graduate committee. Nevertheless, we've had a lot about food. Food determines how far from Earth we can go and how long we can stay. Who didn't see The Martian? You didn't see The Martian? Come on. So, I mean, that's always more instructive than asking who saw it, because it was a very popular, and Grace was right, we got a heck of a lot of media attention, post that movie. And yes, the science was miserable, up to a point. But the arithmetic was actually quite accurate. It was based on the BVAD document, Basic Values and Assumptions document, that determines nutritional and food requirements for astronauts. So they based it on some pretty reasonable science. The one really bad science was the wind. 0.6 kilopascals total is the atmospheric pressure on Mars. It's almost a vacuum as far as you and I are concerned. So to mess my hair would have to be a lot. Nevertheless, a very instructive and thought-provoking piece of movie literature, and one that has stimulated a lot more interest in the issue of food and space exploration. I'm going to talk to you, though, about the technologies required to achieve reliable food life support, and recalling that food is the main limiting variable on space exploration, ultimately, and especially if we decide to go much further away. And I want to put aside a little bit of a misconception, possibly, in a lot of people's thoughts about growing plants in space. None of the work that we do at Guelph has anything to do with a microgravity application. It's my contention that the mass and energy cost, and recall that mass and energy is the currency of space travel. You spend the money in the terrestrial economy. So the mass and energy cost of extensive food production requirements in a low Earth orbit, or even a transit mission to Mars, 6 or 7 months, is prohibitive. We would never invest that mass and energy in a significant amount of food production. We each need between 60 and 70 square meters of plants to provide the nutritional, well-balanced vegetarian diet that we would necessarily require. And to imagine that on a transit mission to Mars, it would be a massive spaceship for a crew of 6 or 8. So not going to happen. Besides, you can always carry enough bacon and Kraft dinner to get you wherever you need to go in the next couple of hundred years, probably, of our exploration requirements. So it's terrestrial bases, the Moon and Mars, where luckily we have an up and a down. So I don't have to deal with the physics and the awkward technology requirements of moving water around and gas exchange under microgravity applications. Completely difficult stuff to do, and I'm quite happy not to consider it. Here's the disclosure thing that I'm pressed to do. Quite self-explanatory, and once again, we all get asked to sign NDAs now. The industry community is trying to steal into the technology development communities, and they all want NDAs. And I explained to them that if you have something that you really don't want me to know, don't tell me, and we'll move on. So, The Martian. It exemplified the challenge, the very profound challenge of space exploration, and the technologies required to defeat some of those challenges and actually get on with the job. We're going to find life on Mars, by the way. You heard it here first. Well, it's almost a certainty, in my mind at least, that when we dig a mile down into a frozen lake on Mars, we're going to find at least the fossilized remains of some microbial community from a couple of billion years ago. So whether it started there and got blasted over to here, or vice versa, is a moot point at this point. But I'm absolutely certain that we'll find some vestiges of some form of life on that chilly planet. But, and I just learned from Grace a few minutes ago that I thought the surface of Mars was kind of chilly with an average temperature roughly of -60, but that isn't the case. Apparently there are some pretty warm spots, so sticking the food out the door as a cooler is not an option. Unfortunately, it was my naive solution. So in Guelph, we started a program back 25 years ago now, SALSA, as was introduced. And that's when we had the first project at the University of Guelph with space in the subtitle. And it's since evolved into a relatively significant contribution, in Canada at least, to the niche field of biological life support in space. And the technologies and research requirements to pursue that goal, being pulled by the technical requirement of going to another planet and surviving. Having said that, I do not yet have a mission to go to the moon or Mars and grow a plant for human life support. No mission, no money. So the funding is entirely derived from industry partners. We have a large range of industry partnerships across the agri-food and aerospace industry sectors, looking to feed on the leading edge of technologies we develop for the broad range of technologies required to be successful in space. One of the big things to remember is you go to space, you can't throw anything away. There's no such thing as garbage. We must learn how to recycle everything, all the carbon, oxygen, water, nitrogen, et cetera, et cetera. We can't do it here on Earth yet, as evidenced by what we call pollution. It's just a word, but it means an ecosystem that isn't good for us. So we have to learn how to do this. One of the biggest technical holes in controlled environment agriculture today is the capability to recycle the hydroponic nutrient solution. And the deficiency is in the technology to sense reliably and indefinitely the quality of the nutrient solution, the quantities of nitrogen, potassium, phosphorus, and all the minor elements that serve as nutrients for plant growth. We do not have the technology to reliably do that today. And hence, when you're a greenhouse grower and you're recycling your hydroponic nutrients every few weeks or so, it gets out of balance because the plants don't eat exactly what you feed them. And so you get an imbalance or a pH modification. And the solution is, well, you throw it out and start again. You can't do that on the moon and Mars. You must learn how to reliably and indefinitely recycle water. It's key. It is almost too critical to overstress. So here's what you need to do in space. And there's not going to be a quiz, well, a little one. But here's the mass and energy. They're the two top of the list. Mass and energy is the currency of space travel. You heard a lot about trying to reduce the amount of food to reduce the mass cost of that component of a space mission. And that's why when we go to Mars and resupply becomes really difficult, not impossible, but really difficult and costly in mass and energy, then we absolutely must develop the bioregenerative, self-sustaining food production system. It's not a question of whether it's a useful or good thing to do. It's an absolute necessity for life support. And you see down here, this list, this is called farming. Light, quality, and quantity, carbon dioxide, temperature, humidity, nutrients, and water. Farming is seeking to homogenize those environment variables as best you can to make plant growth as reliable and productive as possible for life support. So this shouldn't be a surprise to anybody, but putting it into that technical context outlines for you the challenge that we have in controlled environment agriculture, developing the technologies and doing the research that then transfers to, in our case, terrestrial agri-food, because those are our customers today. As I said, I don't have a mission yet, but I will. And in the meantime, we service our training opportunities for grad students and technology developments with industry partners who seek to take the commercial advantage, commercialization opportunities out of the toys that we develop in this regard. So here's where we started actually in 1995, these very first controlled environment chambers. And what I learned very quickly was the limitations in having 2 samples. When you're trying to do research and replicate stuff to the satisfaction of a journal editor, and you're growing soybeans that take 110 days for one experiment, the limitations of 2 boxes to do your research in is quite dramatically limiting. So we've since learned that, and we now have dozens of the darn things. And this is the one we built for the European Space Agency in our research collaboration with ESA's life support program called MELISA. You gotta have an acronym. And typically in the space program, the acronym comes first, right? And then you sort of squeeze in there words that kind of sound like what you do. And hence SALSA. We had a contest among grad students for that one. MELISA is, wait for it, Microecological Life Support System Alternative. We are the higher plant compartment, or the food and atmosphere regenerative element of the MELISA loop, and this is in Barcelona, Spain. And we have a long-standing research relationship with the folks in Barcelona at UAB. Here's the chamber, or one of 5 chambers, that determined the engineering specifications for a greenhouse on the Moon and Mars. It's a hypobaric chamber. It's capable of withholding a vacuum. It has 1.5 square meters of plant growing area. It weighs 8 tons. So if you do the math, remember I said you need about 60 to 70 square meters each for your life support requirements to grow enough food. 8 tons doesn't work for you. Hence, we put quite a bit of effort, and about 15 years ago published the results that plants can handle down to 1/10 of Earth's atmospheric pressure without too much problem at all, being just as productive, providing food, scrubbing CO2, delivering oxygen, recycling fresh water, making you feel good. So those are the main contributions that plants make to life support. And they can do it quite handily at really low hypobaric pressures. So that means that we can consider inflatable structures, low mass inflatable structures for habitats and food production systems. We probably won't do it at 1/10 of Earth's atmosphere, because that's not a shirt sleeve environment for us. And we want to be horticultural mission specialists after all. So the farmers in the crew will want to participate and play with the plants. So it's my understanding from my colleagues at Kennedy that the pressures will likely be around about half of Earth, and that's okay for us. It's certainly okay for plants, happily. Imagine if our answer back in the 2000, 2005, when we were doing this work, if our answer had been, you must have full Earth atmosphere or plants can't do your life support requirements. We're almost done. I mean, that's such a serious speed bump in human space exploration technology requirements that it would almost kill it, a lot of it. We've done a lot more chambers. I'll get into a couple of them here in a second. Here's an array of 9 hypobaric chambers that we used for short-term experiments, a lot of replication, and also developing some rather neat LED lighting systems, so custom high-intensity LED. This critter here can put out 5 times the intensity of the sun within a 1-meter range, which is a ridiculous. It's not even a research tool, but of course, boys with toys. When we built this thing in collaboration with some Norwegian and Canadian investigators, we had to see what it looked like. So it was sitting on the bench. It was an evening. Turned all the lights out, and fired this thing up full blast. And we all had welder's goggles on. It was quite remarkable. The thing almost recoiled. It put out such a, it lit up this entire research facility where all our chambers were. So we've lost our welder's goggles. So we have not been able to demonstrate that again ever since, which is probably okay. It only ended up being that powerful because I needed each monochromatic element, and there's 10 different colors here, from ultraviolet to far red. Each monochromatic component of the spectrum had to have enough intensity, up to at least half the intensity of the sun, to give me an experimental tool that I could use reliably. And when you jam them all together and hit the go button, it's quite remarkable. So we also drift around on the Earth. We're developing technologies for harsh environments in space, but as I said, no mission yet. So the tech transfer is to harsh environments here on Earth. And here we are in the Arctic, on Devon Island, the high Arctic, in collaboration with NASA and the Canadian Space Agency and a number of other institutions. And for 11 years, we operated this greenhouse until just recently, actually. And the objective there was not to really test, miserably cold and bleak and harsh environments. It was to test remote control and automation. So communications were the main thing. And the first year or so, it took us 4 years to grow the first head of lettuce in this greenhouse, 4 years. And one of the major communication issues we had was the satellite that we used for communication was a geosynchronous satellite settled over the sort of high population density of northeastern North America. We were up in the high Arctic here. So this satellite was used to handshake signals that went back and forth in microseconds or whatever. But now suddenly we want it to talk to this critter way up in the Arctic, 76 or 7 degrees north latitude. And the time constant for it sent a signal, but the signal didn't get back. So it took 4 lines of code to fix that, and it took us a couple of years to figure that out. So we struggled with simple little things like that. And those are precisely the kind of technical lessons that you have to learn if you're going to try and do this on the moon, for example, where we'll test drive a lot of this stuff and break it because the moon's 3 days away and not 6 or 7 months away. And resupply and or maintenance and repairs are a little more conceivable in lunar applications. So we've also done it in the Antarctic. This is currently underway. This is the Eden ISS project. It's an 8-country, 14 institution herd of cats. When we have meetings, there's 100 scientists in the room. So this is a project where we're essentially contributing to, we took it down on this boat, but this is the Meyer 3 research station, which is operated by Germany and the German Space Agency as well. And our little critter is out here. They wanted us to go 1 kilometer away from this thing. They lamented finally and allowed us to go only half a kilometer away. And the reason was that our little thing here was going to disturb the snow deposition patterns around the legs of the Meyer 3 station and confound their predictions of how long it would be before it buried itself in snow. So half a kilometer was but what it meant was that this guy, there's the food, but this guy, Paul, who we left down there for a year, he's just come back, he would have to, and you can imagine in the night in the Antarctic, you have to travel that half a kilometer in the snow to get back to your bed. And so there was a safety line that he had to clip himself to, because if it happened to be snowing or really dark or really miserable, you had to be careful. So safety was a profound issue, and that's how we talked them into letting us go only a half a kilometer away. But this is an example of the food that he would produce in that thing. And this was supplementing the diet then of the Meyer 3 crew, the scientists that would be there for 8 to 10 months at a time. And one of the things that we forgot, this was a 4-year project, it's just finished. It's now being restarted in another format. One of the things we forgot, about a year or so before the end of the project, we realized that in the budget, we forgot to provide for the removal and repatriation of the hardware back to Bremen in Germany. Very significant miss. So in other words, it's there, but luckily for us, the Neumeier 3 crew were so enamored of this contribution to their diet, and once again, the psychological benefit of having fresh produce was profoundly important, to the point where they said, okay, we'll look after it, you give us the information on how to run it, the recipes, and then while we search for more money to continue the project, and that's underway now. So this is the green space in it, and then there's a control room that's equally, so it's 2 20-foot containers strapped together. This is the next most recent generation of our controlled environment chamber. It has 8 different LED colors, very high intensity water-cooled LEDs. So we have the capability here of producing a pretty broad range of environment conditions. The key is high fidelity environment control. It determines everything from productivity to nutritional quality to physical attributes. You can fine-tune with environment control. You can fine-tune all of the aspects of how a plant is produced and what it looks like and what it tastes like, what its medical contents can be, et cetera, et cetera. The genetics and breeding are an important element, but the environment control determines what you get. It is so profoundly overpowering of virtually any other aspect of a plant's makeup. So this tool gives us the power to manipulate these environment variables with extremely high fidelity and simultaneously measure the plant's physiological response in terms of photosynthetic gas exchange, respiration, transpiration. So those are very critical metrics to determining the contribution to life support: CO2 cycling, oxygen regeneration, biomass, edible biomass production. And being able to predict that with minute-by-minute measurement capability and the feedback control of high-fidelity environment is an extremely powerful research tool. So we've deployed these in a broad range of applications, all the way from food production systems to medicinal plants. We're growing cancer drugs in tobacco, just for the sheer irony of it, I guess. And also, of course, in Canada now with the changing laws, cannabis is the new kid on the block, and they got money to burn still. It'll slow down shortly, but I'm shamelessly exploiting that phytopharmaceutical industry sector as infrastructure funding to continue to develop the sophisticated tools for this requirement. Here's just an example of what happens when you change the color of the light. You change the way strawberries, in this case, they'll either produce hanging down, sticking up, or being in the middle. And that's just by changing the color of the light. And here's an example of using light and carbon dioxide in these very normal commodities, tomato, lettuce, and pepper. I point out the pepper because here, for example, at roughly a fifth of full sunlight, 40 micromoles per square meter per second, if you don't add any more energy, just take the CO2 from conventional 400 ppm, which is nominal CO2, to 1200 ppm, you double the production, double the edible biomass, if you will. So these are very useful pieces of technology transfer to the environment control and controlled environment agriculture sector. Now here's a high density food production system we developed for applications in northern Canada. Food security is a profound issue in harsh environments in Canada, and it's an economic issue. Canadian taxpayers in the south currently subsidize the delivery of fresh produce to our cousins in the north to the tune of in excess of $120 million a year. And so we air freight strawberries from Mexico That has to stop. I have nothing against the Mexican economy, but I submit that we have the technology, born in space exploration requirements, but we have the technology. It is economically feasible, it turns out. I was surprised to learn that, but it is economically feasible to take a variety of high-priced perishable commodities like strawberries and red peppers and a few other things, and grow them in a snowbank in Yellowknife rather than import them. And so we developed this technology, but I couldn't find anybody in Canada to pay for it. So we went to a different place. We went to the Middle East, where they have an equally profound food security issue, but it's political, not economic. As you know, they have money to burn, and they do, but so they paid for the prototype development, but they also redid our little test drive experiment here with this new red fire designer lettuce. It has a little bit of red anthocyanin in it, and just for the heck of it, seriously, we grew it under red, white, and blue light. And when we sent it to Kuwait, they replicated that experiment to see if they could get the same nutritional content, the same productivity, the same data that we got. This is what you get. These are genetically not identical, they're not clones, but they're F6, F7 varieties. So these are genetically the same. They have the same, all that long list of environment variables that I told you, except the color of the light. That's all that's different here. This one under red light is twice the dry biomass of, especially this one, and almost twice the dry biomass of the one under the white light. And as you can see, there's some profound differences in anthocyanin expression. And of course, grad students being what they are, they did a blind taste test, and there's a dozen grad students in the lab, and they sat there and with 100% reliability said, that's the blue one, that's the white one, that's the red one. So there's a taste, a very significant taste difference. There's a color difference. Color and taste are secondary metabolites, as are the cancer drugs, the proteins for cancer drugs that we're developing, as are the cannabinoids in cannabis, THC, CBD. These are secondary metabolites. So I have a tool to quite precisely play with the secondary metabolite content of these plants, and more particularly, especially with phytopharmaceutical plants, standardize the profile of medical compounds, which allows those plants to achieve the lofty status of a conventional pharmaceutical commodity, which they aren't today. Now, this is a quick video of a pilot scale demonstration of this. So this is coming down to practical applications now of these technologies. This is a little cartoon, but this actually exists, and I'll show you the picture in a second. And what happens here is, this is a bit of a gradient. This is the top of the hill, and this is the bottom of the hill, and we're looking at, say, romaine lettuce, so that the time from the top of the hill to the bottom is 8 weeks. And then the robotic lift takes the mature product out here, and then it goes off on a conveyor to be packaged up in the big boy bags, and off you go. And then at the other end, the seedlings get loaded. And depending on the commodity, you could have a different commodity on each level. This is a 7-level system. You could have different times, different commodities, different environment conditions within reason on these different levels, and produce a wide range of, in this case, microgreens or herbs or food crops. Here it is in actual operation in Toronto in a warehouse, in an industrial warehouse in Toronto. And this little company that is collaborating with us on using and deploying this pilot of our system is called We the Roots, and they have sold everything they can possibly grow, regardless of what it is, for the next 2.5 years to local restaurants, high-end, celebrity chefs, and that sort of. This is what it looks like. I'm going to quickly go through, and this is the scale that it's aimed for. 2 of these projects are currently under construction, one in St. Catharines, Ontario, and one in New Jersey. They'll be operational probably early next year, but consider the scale here. I mean, they were trying to replace a field in Salinas, California for lettuce production. And one of the big costs, obviously, is the energy. But one of the big benefits is the food safety. You can much more reliably ensure food safety in a system like this than you can in a field in Salinas. And I think I'm going to run right to the end here. You've seen a variation of this take-home message today from our speakers already. Basically, as I've said, the technologies that we require to go to space and survive are precisely those that we are almost legislating ourselves into here on Earth, especially in agricultural jurisdictions. Recycling water, not fouling the earth with nitrate fertilizers and pesticide residues. We can do it. We have the technology. We don't yet quite have the political will, but it's coming. So, and we'll use that pull of space exploration as an economic engine in the agri-food sector. That's how this whole thing must work, and eventually it'll probably make life better for all of us. Thanks.